All right. So yesterday we talked a little bit about centripetal force and like our most straightforward tension problems. Today we are going to talk about centripetal force and a really cool application, which is racetracks. So you may or may not know this, but a race car going around a track is a really common application of centripetal force. And so we're going to start by looking at what force is providing the centripetal force in this problem. And then doing a couple of practice problems. And then we're also going to look at qualitatively what are some things we can do to get higher and higher speeds at racetracks. All right, let's go ahead and get started. So when I have a car that is traveling around a circle, the thing that is providing the force, and if you want to think about this and understand it, think about a hot day versus an icy day. When you try to turn in a circle on a hot day, there's not a problem, right? You're able to do it and your tires stick to the road really nice and you're good to go. But on an icy day, if you try to make the same turn, you might end up not quite making it. And as a result, you may end up sliding off the road. And if you've ever tried to turn like a really tight turn in a parking lot in the ice, you will know this. That's because the force that's giving us the uh, centripetal force in this case is friction. Now, we may remember friction from before, and I will link a card to my video about friction right here. But friction has kind of two components. It has the coefficient of friction, which tells you how much two surfaces stick together, and it's a number that's always between 0 and 1. And it has the normal force, which for most cases, so usually, is just the mass of the car times acceleration due to gravity. We will look later on when we're talking about tips and tricks to go faster in a car. We'll talk about that normal force because it's one of the best ways to do it. So in the problems that are going to follow, this force of friction is going to be serving as our centripetal force. And I want to say for tires in the ground, uh, if we are looking at sort of a really nice warm day, we're usually looking at a mu between zero point 0.7 to zero point 0.8. Really pretty high. Honestly, rubber on the road is one of the um, best case scenarios for friction. It's why we make tires of rubber, actually, is because it's a way that we can maximize that friction. If it's raining, we're looking at more 0.5 to zero point 0.6. And if it is icy, we are looking at like 0.1 to zero point 0.2. And I want to say, uh, given that I am somebody who talks to a lot of young drivers, like keep that in mind when you're driving, how big of a change that is. You might have 1/8 as much friction in the ice as you do normally. And so you'll often see people driving a lot slower, but there's a really good reason for that. All right, let's do a couple of problems with this, and then we're going to talk about qualitatively some of the ways that we can play around with this and that Formula One engineers do. So I'm going to say that I have a 1,000 kilogram car traveling at 15 meters per second on a 20-meter radius turn. What coefficient of friction is needed? Go ahead and pause here if you want to try to work this problem on your own. Now, when a lot of people look at something like this, the very first thing that they usually want to do is they want to figure out what we have the variables to solve for. We have a mass, we have a velocity, we have a radius, and so for most people, the temptation is to go straight to mv squared over r. And that's not wrong. It'll get you where you need to go eventually. But I'm going to give you kind of a tip here for all centripetal force problems, which is that it's really best if the very first thing you do is figure out what force is providing the centripetal force and then set those two expressions equal right away. And in this case, we know that the force of friction is providing the centripetal force. So right off the bat, I can say that the force of friction equals centripetal force, which means that mu times m times g is equal to mv squared over r. Now, one reason I like this is, as you're about to see, it lets us solve a problem in an abstract way first, which gives us something that will like always, always, always be true. Um, but it also shows us that the mass cancels out on both sides. Now, why is that important? It means that no matter how heavy my car is, I will always get the same answer. So I could be in a 500 kilogram sports car, I could be in a 1,000 kilogram family SUV, I could be in a 2,000 kilogram truck, and they're all going to give me the same answer for the coefficient of friction that's needed. And as somebody who trained as a civil engineer, that's really useful because what does that let me do? It lets me design a turn that will work for any car. And that's essentially what civil engineers have to do on the road. They have to figure out a way to make the road safe for all the cars that are on the road. And so if the mass of the car was a really big determining factor in that, then they would have to really think about, well, are trucks even allowed on this road? Are sports cars even allowed on this road? And while there are some parts, usually collisions, where mass plays a role, when it comes to designing the road itself, it plays very little. So now that we've canceled out our masses, we get mu g equals v squared over r. Now, if you are somebody who is relatively new to algebra, I would say right away start plugging in numbers that you know here. However, I would recommend if you are pretty good with algebra. So if you want to do this in a more abstract way, what we would do is we are going to try to get the mu, which is what we're trying to solve for, all alone. So we'll divide both sides by g, which will give us mu over here and v squared over gr over here. And so here we can plug it in. 15 squared over 9.8 times 20. And we'll end up with 15 squared is 225. And there on the bottom, we get 196, which tells us that the answer here is 1.15. And my response when I see that is, oh no. Why? Because the coefficient of friction needs to be between 0 and 1. And that is, by definition, what we learned. Anything stickier than that, we're using like glue or a tape or something like that. So what does that mean? It means you can't go that fast. So let's kind of turn that question around. How fast can I go given all of the other previous information, if my coefficient of friction is only going to be 0.8. And here's where I really like having uh, done this abstractly, because this part is still true, even though I am changing some of the variables around. Mu equals v squared over gr is still true. So I'm going to say mu equals v squared over gr. I can rearrange actually because I want velocity is what I'm going to solve for. So I'm going to multiply both sides by gr. So v squared equals mu gr. So 0 0.8 times 9.8 times 20. And what do I end up with? I end up with a v squared of 156.8, which means that my velocity is 12.5 meters per second. So I just have to go a little slower. All right. Just like with our tension problems, we can ask these with lots of different variables being withheld, but we can always use the same technique to solve it. Now let's talk about some of the tricks that we use to go faster with race cars. The first one has to do with this idea that the force of friction is equal to the mu times the normal force. And when we talked about normal force, which I will link here, when we talked about normal force, we remember that like if it's just the force of gravity acting on this box, then normal force only has to resist the force of gravity. But if I add some extra force, maybe by pushing down on it, well, now the normal force has to be a lot bigger to compensate for both the push and the force of gravity. So what that means is if I push down on my car, I can increase my normal force beyond just m times g. And if I increase my normal force, that increases my force of friction. This is why we have what are called spoilers on the back of cars. So if you look at a car and this is the license plate, and it has like one of these fins up over the back, this is called a spoiler. And it works exactly the same way that an airplane wing works, but in reverse. So with an airplane wing, basically the difference in air pressure above and below results in something that we call lift. And with a spoiler, it's just upside down so that the difference in air pressure above and below results in something we call downforce. It's actually pushing the car down into the ground. And actually, the faster the car goes, the harder it pushes down. So that is one trick we have to kind of artificially increase that force of friction. And that will allow us to go faster. The other thing we have is what we call a banked turn, which if you think about putting like a box on a ramp, you know it's going to fall down towards the bottom of the ramp. Well, what if instead of having a flat surface to drive on, we have a surface where our left wheel is lower than our right wheel? Then the whole car is going to be tempted to move towards the center. And it actually has to do with some amount of gravity. Take AP Physics if you want to know how that works out. But some portion of gravity is pulling the car towards the center. So what does that mean here? It means that we aren't just dealing with friction, we're also experiencing a force of gravity. And both of them are contributing to the centripetal force, which means that we have more force and therefore we can go faster. So these are some of the really cool things that engineers in Formula One work with. And in a racetrack, like Talladega has a 33-degree banking on its turns. Normal roads are also banked, not always, but especially if you get ones that are turns and twists and turns, and especially if they have to be kind of tight turns, they will often have In that case, more like a 2 to 5 degree banking. But it actually really significantly increases the speed that you can go through those turns at. All right. Next time we'll talk about universal gravitation. And then after that, we'll talk about how that can be used as a centripetal force to create orbits. Thanks. Bye.